Hi dear, welcome back. So I will continue from the last live that have solved some problems of advanced electronics for my upcoming from final exam. Now I will continue the solving the questions of that advanced course. So let's start. So question was, how does the crystal structure of the granite influence the dielectric properties? The summary of the question is, the structure of barium enables high dielectric constant through titanium ion polarization. Small grain center and the perovskite structure of barium titanate enables high dielectric constants through titanium ion polarization, phase transition, and small grain sizes further enhance trick properties. So there are four main points that influence dielectric properties. One is perovskite structure, titanium in the center of octahedral sites. The unstable titanium ion occupies the six off-center positions in the octahedral site, resulting in spontaneous polarization. Then the polarization, high polarization arises from the alignment of titanium ions when an electric field is applied, leading to a high dielectric constant. Phase transition, it changes in crystal structure from cubic to tetragonal, which can significantly affect the dielectric behavior. And the last is grain size. If the grains are small, the dielectric constant will increase as the internal stress and different wall also increase. So, what are the what are the talking said in the slide? Different polymorphs of barium titanate and accompanying changes. There is a graph showing the dielectric constant. Dielectric constant is varying with the temperature. Cubic to tetragonal, then tetragonal to orthorhombic, and orthorhombic to rhombohedral. The highest dielectric constant is in around 401 Kelvin when the structure is cubic, and 1 Kelvin when the structure is cubic increases with the change of structure. Then again, when the temperature is decreased further, the dielectric constant decreased more and from tetragonal to orthorhombic, and when the temperature and phase transition. The temperature brings the phase transition, and the phase transition brings the dielectric properties change. Again, the polarization of titanium ion also changes the dielectric properties. The grain size changes the dielectric properties, and the perovskite structure itself changes the dielectric properties. Okay. Discuss the effect of temperature and grain size. This is the next question. So the next question is, discuss the effect temperature. So let's discuss the effect of temperature, and we'll choose the slide 14. Discuss the effect of temperature and grain size on the dielectric constant of barium titanate. Previously, I have said that the grain size it decreases, the density and internal stress also increase, and the dielectric constant increase along with the grain. If the grain size is small, grains are small. If the grains are smaller, internal stress will be increased, and the demand one intensity will be increased, and the constant will be higher. And from the temperature, directly constant of temperature change in temperature alters the crystal structure of barium titanate, affecting the polarization. At cool temperature, barium titanate transitions between ferroelectric and paraelectric phases, leading to significant variation in dielectric constant. Grain size: smaller grain produce higher dielectric constant due to internal stress and increased number of domain walls. Larger grains have fewer boundaries. Larger grains have fewer boundaries, reducing resistance to current flow and lowering the dielectric constant. If the grains are large, the grain boundaries and reducing the resistance to current flow. So it will allow the current to flow, and it will lower the dielectric constant. So we do not want to we do not want to resist the current. So sorry, we want to resist the current. So we do not want to reduce the resistance to the current. We want to increase the resistance to the current, and uh, lowering the dielectric constant. So finer grains produce high dielectric constant due to presence of internal stress, due to increase in the number of domain walls. Large grains have fewer grain boundaries, less resistance to process. 1 micrometer grain size in the up position. So the relative permeability of 1 micrometer will be large. Temperature dielectric constant peak at Curie temperature due to consumption. Grain size: smaller grain increase dielectric constant due to more domain walls and internal stress. So the appropriate answer will be the proper one. Effect constant of barium titanate. One temperature changes in temperature alter transitions between ferroelectric and paraelectric phase. Ferroelectric and paraelectric phases leading to significant in the dielectric constant. So it changes from cubic to tetragonal to orthorhombic to rhombohedral. Cubic is at above 120 0 to 120 degrees centigrade. 0 to minus 90 degrees centigrade is octahedral and minus 90 degrees centigrade is rhombohedral. What is the dielectric constant in cubic phase? What is the dielectric constant in tetrahedral phase? What is the dielectric constant in orthorhombic phase? And what is the dielectric constant of rhombohedral phase of barium titanate? Is a dielectric the dielectric constant value of cubic is 6000, tetragonal is 3000, and orthorhombic is below 3000. The dielectric constant value of orthorhombic and rhombohedral is the dielectric constant values. Okay, before that comes, we can talk about the grain size. Grain size. We will also draw the picture. Grain size. Smaller grains produce a higher dielectric constant due to internal stress and increased number of domain walls. Number two, large grains have fewer grain boundaries. Larger grains have fewer boundaries, reducing resistance to current and lowering the dielectric constant. Temperature. The dielectric constant peaks at the what is the summary. So there must be a graph also. Summary. summary dielectric constant for the temperature. For the temperature, there is a summary. For the temperature, dielectric constant peaks at the Curie temperature due to phase transition. Dielectric constant peak peaks at the Curie temperature due to phase transitions. Number two, grain size. Smaller grain size increase dielectric constant. Grain size. Smaller size increase, increases dielectric constant due to more domain walls and internal stress. At cubic phase, the dielectric constant is 100, 200 to 500. 200 to 500, 500 to 1000. From the picture, we can see that cubic 10,000, tetragonal 4,000, rhombohedral 2,000. Our major concern is the graphs. Here is the graph that will explain the property of barium pregnant with the temperature. 6,000, 3,000, nearly 6,000 in at cubic phase, then it is quite 4,000 in the next phase, and nearly then decreases. Sometimes it fluctuates. Graph fluctuates. From cubic C, Ts is equal to 0, cool temperature greater than 400 Kelvin. Then 200 Kelvin, then 200 Kelvin, then 100 Kelvin, then 0 Kelvin. At 401 Kelvin or 394 Kelvin, the fluctuation is seen at 285 Kelvin and 279 Kelvin. These peaks are observed. At 181 Kelvin or 196 Kelvin, these peaks are observed. So this is the different. Now, most in cases, their dielectric constant in 6,000 is in cubic, 4,000 when it is tetragonal PS001. In orthorhombic, it is 3,000. It is 3,000 at orthorhombic phase PS011. At uh, at rhombohedral, PS is 111, and uh, in 0 it is 100. P is 0 because 001, 011, 100. At rhombohedral, uh, the cool temperature is below 3,000, which is sometimes below 3,000. Below 3,000 is 500, 400, 300, 100. Then excuse me. The structure We can see the structure looks like this in cubic. Titanium is in center. Cubic titanium is inside. Titanium it is cubic, and PS is equal to 0. A tetragonal goes up slightly up, slightly. PS it is PS in tetragonal 001 and in the thermic 01. And when it comes to this orthogonal, it moves, the titanium moves through the plane. This is equal to 1011. And when the titanium ion goes toward the diagonal, goes toward the diagonal, you can say that it is rhombohedral, and this is 111. These are the all structures. But I doubt about the direct constant values. What are the direct constant values is 6,000, 4,000, 3,000, then below 3,000. This is how the direct constant decreases in the barium pattern structure. Now it comes the grain size, how the grain size fits. The grain size of barium titanate has strong influence on dielectric constant. Finer grains produce higher dielectric constant. The dielectric constant is 5 into 10 to the power 3 in 1 micrometer. Then it decreases for 3, then 15 micrometer, then 50 micrometer. Finer grain size produce higher dielectric constant due to the presence of the internal space. Due to the increase in the number of domain blocks, larger grains have fewer grain boundaries, less resistance to current flow. So we want lower grains. Time to draw the graph. In x-axis, temperature degree centigrade, 0, 100, 200. X-axis, temperature degree centigrade, 0, 100, 200. between 100 and 200, the temperature goes into peak. Next six is relative permeability. Keep it. Okay. Mm, in the summary, you can say that dielectric constant peaks at the cool temperature due to phase transitions. Grain size, smaller grain size increases dielectric constant due to more domain walls and internal stress. Discuss the dielectric effect temperature, grain size, and the dielectric constant of barium titanate. Polymorphs of barium titanate. Compare the dielectric constant of different polymorphs of barium titanate. What are the polymorphs of barium titanate? Polymorphs of barium titanate. Compare. Where is the question? Compare the compare the dielectric constant. Compare the dielectric constant compare the dielectric constants of different polymorphs. Compare the dielectric constant constants of different polymorphs of barium titanate.